About 100 years ago, two epidemiologists wrote a seminal paper in which they presented a general mathematical model that would describe how epidemics spread, reach their peak, and eventually die out. Recognizing the complexity of their general model, which involved integral differential equations, Kermack and McKendrick, the two authors, developed in the end of their paper a significantly simplified version of that model, which resorted to unrealistic assumptions for mathematical convenience, yet the model could still make some very useful predictions. The simplified version that is, became the celebrated SIR model. The SIR model predicts correctly things that became household names in the COVID-19 era, such as herd immunity or the total number of infected individuals throughout an epidemic. However, the SIR model misses one key point: the peak number of individuals to be infected throughout an epidemic. It misses that by as much as a factor of 2. This shortcoming of the standard SIR model may have severe implications when one tries to keep low the peak number of infected individuals or to secure resources for their treatment. Actually, related efforts to lower the peak during the COVID-19 epidemic became widely known as flattening the curve, another household name. The reason for this failure to get the peak of infected correctly is that the standard SIR model unrealistically assumes that among infected individuals, most will recover in 0 time. Now, by itself, that absurdity would not be a problem. Indeed, all models are wrong, but some are useful, said George Box, a dictum that applies well here. But wrong model predictions for the peak of infected population fraction indeed compromise usefulness of the SIR model. To address that, we borrowed concepts from the mathematical theory of control systems and blended them with epidemiology models to develop in a series of 2 related papers a refined version of the SIR model, which is just as simple as the original SIR model. It involves only 1 or 2 additional parameters, and it is easy to estimate from data and captures the peak of the infected very well. We believe that it is this model that should become the standard to be used in efforts to model epidemics related to data and to guide management and control of infectious diseases. This would be a worthwhile task.